Somewhere beyond the reach of sunlight, in a darkness so complete that even starlight begins to feel like memory, a small machine continues to move. It has been moving for longer than most human lives last. It will keep moving long after every one of us is gone. It has no eyes, and yet it once looked upon worlds no living being had ever seen. It has no voice, and yet it speaks faithfully every single day in a language of radio waves that takes over 20 hours to cross the emptiness and reach us. It has no heart, not in the way we understand hearts, but it carries something remarkably close to one. Picture it now drifting. Its gold-plated surface no longer gleams because there is no sun bright enough out here to make anything gleam. Its instruments, most of them, have long since gone quiet, switched off one by one to save the last flickers of power. It moves in silence through cold that has no real name, at a speed that would carry it across the entire United States in under 3 minutes. And yet, for all that motion, all that distance, it is not really alone, not in the way it might seem. Because this machine was never simply metal and wire. When engineers on Earth assembled it decade after decade ago, they were not just building a scientific instrument. They were building something closer to a proxy, a traveler sent in our place, carrying pieces of us into realms our bodies could never survive. Its cameras were meant to be our eyes. Its sensors, our fingertips, reaching out to touch the swirling clouds of distant giants. Its long silence and its long journey were meant to be our patience, made physical, made permanent, made real. Onboard, fixed to its side like a keepsake tucked into the pocket of someone leaving home for good, rests a golden record. A phonograph disc, the kind of thing that might once have played in a quiet living room on a Sunday afternoon. Except this one was never meant for a living room. It was pressed with the sounds of Earth itself, waves breaking on a shore somewhere, wind moving through grass. A mother's voice speaking gently to her newborn child, music from cultures scattered across every continent, chosen with the aching hope that somewhere, someday, something might listen. We will return to that record. Its full story is one we will save, and it deserves to be saved for later in our journey together, when we understand everything this spacecraft endured to make that message worth sending. For now, it is enough to simply sit with the image of it, a single, small, human-made object, smaller than a car, drifting through a darkness so vast that words like far and distant lose most of their meaning. It has no engines firing anymore. It doesn't need them. It was given exactly the push it needed many years ago, back when the world it left was still figuring out something as ordinary as a handheld calculator. Out there, this spacecraft does not feel isolation, of course. It cannot feel anything at all. But if we allow ourselves just for a moment to imagine what its journey means rather than simply what it is, something quietly moving emerges. A machine built by hands that are now mostly still, launched by minds that mostly belong to another century, continuing to travel outward not because it chooses to, but because nothing has yet told it to stop. It carries no passengers, and yet it carries almost everything that matters to us. Our curiosity, which refused to be satisfied with only the world beneath our feet. Our fear, quiet but real, of being alone in an indifferent universe. And our hope, stubborn and enduring, that being alone might not be the final answer after all. This is the story of how that small machine came to exist. How a narrow, fragile window in time, open for only a few short years, convinced an entire generation of scientists to risk everything on a single, audacious voyage. How two identical twins were built to carry out that voyage together, only to be separated forever by the pull of distant worlds. And how, long after their original mission was declared complete, they kept going anyway, past the giant planets, past the edge of everything the sun can touch, and out into the true, unmeasured dark. But before any of that could happen, before a single rocket could leave the ground, there was a much quieter kind of drama unfolding. Not among the stars, but in rooms full of chalkboards and slide rules, where a small group of scientists noticed something remarkable about the way the planets happened to be arranged. A window. One that would not open again for another 176 years. They understood almost immediately that if humanity did not seize this moment, it would not come again in any of our lifetimes. not in our children's lifetimes, not even in our grandchildren's. That race against a closing door in the sky is where our story truly begins. In the early 1960s, in a modest office at what would soon become NASA's Jet Propulsion Laboratory, a graduate student sat before a set of hand-drawn orbital charts, tracing the slow, patient arcs of the outer planets across the decades. His name was Gary Flandreau, and what he found, almost by accident, would go on to shape the next 50 years of human space exploration. At the time, no one had asked him to imagine a mission to the outer solar system. He had been given a far smaller task, to study trajectories for possible probes to Jupiter, using the gravity of that giant planet to bend a spacecraft's path and fling it onward. This idea, using a planet's own gravity as a slingshot, was not entirely new. Scientists understood the principle. What Flandreau noticed, however, was something no one had fully appreciated. Every so often, the outer planets, Jupiter, Saturn, Uranus, and Neptune, drift into a rare and specific alignment. Not closed together in space, but positioned in such a way that a single spacecraft, launched at just the right moment, could use the gravity of each planet in sequence to swing onward to the next. Jupiter could fling a probe toward Saturn. Saturn could fling it toward Uranus. Uranus could fling it toward Neptune. A single launch, a single spacecraft, could in principle visit all 4 giant planets in one continuous journey, using almost no fuel of its own beyond what was needed to leave Earth. Without this alignment, a mission to Neptune alone, using conventional propulsion, would take roughly 30 years. With it, the journey could be compressed into about 12. This was already a striking discovery, but then Flandreau calculated something else, something that turned an interesting orbital curiosity into a matter of real urgency. This particular alignment, precise enough to make what would later be called the Grand Tour possible, occurs only once every 176 years. Sit with that number for a moment, because it is worth truly understanding, not just hearing. 176 years is longer than the entire span of powered flight, from the first fragile hop at Kitty Hawk to the day you are listening to this now. It is longer than the lifetime of any person who would ever work on the mission, longer than the careers of their children, longer even than most of their grandchildren might live to see. The window that had just opened, quite unexpectedly, in the ordinary slow wheeling of the planets, would close again sometime in the middle of the 22nd century. Anyone who missed it would not get a second chance. Their children would not get a second chance. It would be, for all practical purposes, gone. There is something almost unbearably poignant in that fact when you let it settle. The universe does not usually offer humanity neat deadlines. Stars do not announce when they are about to change. Galaxies do not politely wait for our instruments to catch up. And yet here, quietly in the numbers on a young engineer's chart, was something very close to an invitation with an expiration date. The solar system itself seemed to be saying, gently but firmly, that this moment, this particular scattering of decades in the 20th century, would be the only opportunity for a very long while. Word of Flandreau's discovery moved slowly at first, the way important things sometimes do, through internal memos and quiet conversations among engineers who understood immediately what it meant, even if the wider world did not yet grasp its significance. Excitement began to build inside JPL, that particular kind of excitement that scientists feel not loudly, but in the careful, focused way they return again and again to a set of numbers, checking and rechecking, almost afraid that some error will make the beautiful alignment disappear. It did not disappear, the math held, and so began one of the more remarkable periods of quiet, sustained ambition in the history of exploration. Engineers began sketching what such a mission might look like. Early plans were audacious, almost dreamlike in scope. A fleet of sophisticated spacecraft launched across several years, each one visiting all 4 giant planets in turn, carrying instruments that did not yet exist, built to survive a journey longer than most engineering projects had ever attempted. But ambition alone does not launch spacecraft, funding does, and funding in the real world is never quite as patient as orbital mechanics. As the 1960s gave way to the 1970s, the political and financial climate around NASA shifted considerably. The Apollo program, having achieved its extraordinary goal of landing humans on the moon, was winding down, and with it went a great deal of the public enthusiasm and the public money that had carried the space agency through its most ambitious years. The original Grand Tour concept, with its fleet of purpose-built spacecraft, proved simply too expensive for the era it was born into. It would have been easy at this point for the whole idea to quietly die. Many similarly bold proposals from that period did exactly that, reduced to file folders in some archive, remembered only by the handful of people who once believed in them. But the scientists and engineers who had spent years with these trajectories in their minds were not willing to let the opportunity simply slip away. If a full fleet was politically impossible, they reasoned, then perhaps a smaller, more modest mission could still capture the heart of the idea. Not 4 spacecraft, but 2. Not a formal visit to every planet with every instrument imaginable, but a more focused expedition, still built to take advantage of that same irreplaceable alignment, still capable of reaching at least Jupiter and Saturn with certainty, and quietly designed in its bones to be able to continue on toward Uranus and Neptune if the spacecraft and the funding and the political will all managed to survive that long. This was the compromise that would eventually become Voyager, smaller in ambition than the original dream perhaps, but no less audacious in what it dared to attempt. 2 identical spacecraft rather than a fleet, a tighter budget, a narrower official mandate, but the same underlying, almost stubborn commitment to not letting this particular door close unopened. Approval for the mission finally came in the early 1970s, and with it came a new kind of pressure, one measured not in dollars or political goodwill, but in something far less negotiable, time itself. The alignment of the planets does not wait for budget approvals or committee meetings. It does not care about engineering setbacks or testing delays. It simply continues its slow, ancient rotation, indifferent to human deadlines, and if the spacecraft were not ready, if they were not built, tested, and sitting on a launch pad within a very specific span of years, the entire opportunity, the one that would not return for a century and 3/4, would pass by unused. Engineers who worked on the project during this period often described a very particular kind of urgency, different from the frantic sprint of a crisis, but no less demanding. It was the urgency of knowing that they were not just building a spacecraft for their own careers, or even for their own era, but for something closer to a promise made across generations. If they succeeded, people not yet born would eventually look at photographs of worlds no human eye had ever properly seen. If they failed, if a rocket faltered or a spacecraft was not ready in time, no one currently alive, and very possibly no one for 6 or 7 generations afterward, would get another chance at that particular alignment. It is a strange kind of weight to carry into daily work. Most of us build things, or write things, or raise things, with some reasonable hope of seeing the results within our own lifetime. The engineers preparing Voyager were building something with the understanding that its true, final meaning might not be fully felt for centuries, long after the last person who had ever touched its circuitry had themselves become part of the past. And so, through the middle years of the 1970s, in clean rooms and testing facilities across the country, that quiet, patient urgency slowly turned into something physical. Metal frames took shape, circuits were soldered, instruments, each one designed to survive years of vacuum, radiation, and extreme cold, were carefully fitted into place. The window in the sky remained open for now. But everyone involved understood, without needing to be reminded, exactly how narrow it truly was. What they were building in those years was not simply a machine. It was, in its own way, a kind of proxy for humanity itself, a stand-in sent to do what no human body could yet survive doing. And the story of how that proxy came to be assembled, piece by careful piece, is where we find ourselves next. Inside the clean rooms of the Jet Propulsion Laboratory, in the middle years of the 1970s, something unusual was taking shape. It did not look like much at first. Skeletal frames of aluminum and titanium, bare circuit boards laid out on tables like the disassembled organs of some creature not yet given form. Engineers moved among these pieces in white coveralls, speaking in the hushed, careful tones people use around something fragile or something sacred or both. What they were building would eventually be called Voyager 1 and Voyager 2, two spacecraft, identical in nearly every respect, built side by side, almost like twins conceived and raised together, destined nonetheless to live entirely separate lives. But in these early months, they were not yet travelers bound for distant worlds. They were simply an enormous, patient puzzle, and every person in that room understood that the smallest overlooked piece could mean the difference between a mission that succeeded for decades and one that failed silently, invisibly, sometime after it was far too late to send a repair crew. Because that was the strange, defining truth of this project, one that shaped every decision the engineers made. Once these spacecraft left Earth, no human hand would ever touch them again. There would be no service calls, no replacement parts, no second attempt. Whatever imperfections were built into these machines, however small, would travel with them for the rest of their existence, whether that existence lasted 5 years or 50. This is, in many ways, what separates the engineering of a spacecraft like this from almost anything else built by human hands. A car can be brought back to a garage. A bridge can be inspected and repaired. Even the most complex earthbound machines exist within reach of the people who built them. Voyager would not. Every system had to be designed not just to work, but to keep working without maintenance, without adjustment, across a span of time longer than most marriages, longer than most careers, in an environment more hostile than almost anywhere humans had ever sent a machine before. Consider for a moment the challenge of simply powering such a spacecraft. Solar panels, the obvious choice for a spacecraft near Earth, become nearly useless in the outer solar system, where sunlight is so faint by the time it reaches Jupiter that it carries only a small fraction of the energy it does here. By the time a spacecraft might reach Neptune, sunlight would be roughly 900 times weaker than what warms our own skies. Solar power, in other words, was never a real option for this mission. Something else would have to keep these machines alive. The answer the engineers settled on was almost startling in its elegance and slightly unsettling in its implications. Each spacecraft would carry a small quantity of plutonium-238, a radioactive material that generates heat naturally as it decays, slowly and predictably, over many decades. That heat could be converted into a steady trickle of electricity, enough to power the spacecraft's instruments, its transmitter, its onboard computers, all without a single moving part, all without any dependence on sunlight whatsoever. In effect, each Voyager would carry a small, quiet, radioactive heart, one that would keep beating long after any battery or solar panel would have gone dark. It is a peculiar thing to consider that the very same physical process responsible for some of humanity's most destructive inventions was here being used for something profoundly gentle. An ember tucked into the body of an explorer meant only to keep it warm and awake as it wandered through the dark. The instruments this radioactive heart would power were themselves marvels of a very particular kind of engineering restraint. In the 1970s, computing power was a tiny fraction of what even a simple modern device carries today. The engineers who designed Voyager's onboard systems had to accomplish extraordinary feats of data collection, navigation, and communication using computers with less memory and processing capability than what runs a modern kitchen appliance. Every instruction had to be written with obsessive economy. Every measurement had to be planned in advance because there was no possibility of simply improvising a new command on the fly and hoping the spacecraft's hardware could handle it. And yet, despite these constraints, the instruments the engineers designed were remarkably capable. Cameras tuned to capture detail across vast distances. Spectrometers designed to analyze the chemical composition of distant atmospheres from nothing more than the light those atmospheres reflected. Magnetometers, sensitive enough to detect magnetic fields far weaker than anything found on Earth. Plasma detectors, capable of sensing the thin, charged particles that stream outward from the sun, thinning further and further the deeper into space a spacecraft travels. Each of these instruments, in its own way, was a kind of translated human sense. The cameras were eyes, adapted to see wavelengths and distances no human eye ever could. The spectrometers were something closer to a tongue or a nose, capable of tasting the chemical fingerprint of an alien atmosphere from millions of miles away. The magnetometers and plasma detectors were subtler still, closer to a kind of skin, sensitive to forces humans cannot feel directly at all, the invisible currents and fields that shape so much of what happens in space. Piece by piece, the engineers were not simply assembling a scientific instrument. They were constructing something closer to a sensory surrogate, a body built specifically to perceive what no human body ever could survive perceiving directly. Every choice, from the plutonium heart to the finely tuned cameras, was made in service of a single underlying goal: to create something that could travel where we could not and still bring back what it found. There was also, built into the very core of these spacecraft, a kind of stubborn redundancy, a philosophy of expecting failure and refusing to let it be fatal. Critical systems were often duplicated, so that if one component failed silently, invisibly, light years from any repair technician, a backup could take over without any interruption to the mission. Engineers spent countless hours imagining every conceivable way something might go wrong: a jammed instrument, a stuck antenna, a computer glitch triggered by a stray burst of cosmic radiation, and then designing quiet, automatic solutions for each scenario, tucked into the spacecraft's programming like a series of careful contingency letters, written and sealed long before they might ever need to be opened. This obsessive preparation for a threat that might never fully be understood in advance says something quietly moving about the people who built these machines. They were not simply engineers solving a technical problem. They were, in a very real sense, parents preparing a child for a journey they themselves could never accompany it on, doing everything within their power to anticipate dangers they could only partly imagine, knowing that once the spacecraft left their hands, it would have to face whatever came next entirely alone. And there was one more piece, one final addition to these spacecraft that had nothing to do with survival or navigation or scientific measurement at all. Fixed to the side of each Voyager was a golden phonograph record, carefully sealed against the ravages of space, engraved with instructions so painstakingly simple that its creators hoped even an intelligence with no shared language, no shared biology, no shared history with humanity at all, might someday be able to decipher how to play it. This record was not required for the mission to succeed. It served no scientific purpose, activated no instrument, corrected no trajectory. And yet the team fought hard to include it, understanding perhaps that a spacecraft built entirely of eyes and ears and careful redundancies was missing something essential, something that no instrument alone could capture. Not simply what the universe looked like from an outsider's perspective, but who exactly had sent this small, patient traveler outward to see it. We will return to that golden record later in our journey, when its full story can be given the space it deserves. For now, it is enough to know it was there, riding quietly alongside every circuit and sensor, a small piece of home tucked into the side of a spacecraft that most of its creators understood they would never see again after launch. By the middle of 1977, after years of design, testing, and careful, patient assembly, both spacecraft were essentially complete. Twins built side by side, sharing nearly every design detail, yet destined to follow entirely separate paths through the decades ahead. They sat now in their final preparations, each one representing not just a machine, but the accumulated hope, caution, and quiet love of thousands of people who had spent years imagining every possible way to keep something so small and fragile alive across a journey so impossibly vast. Soon it would be time to say goodbye. There's a particular kind of silence that settles over a launch site in the final hour before liftoff. It is not the silence of emptiness, because the pad is anything but empty, crowded with steel and fuel and the accumulated labor of thousands of hands. It is instead the silence of held breath, the kind that falls over a room just before someone speaks words that cannot be unspoken, or over a doorway just before someone steps through it for the last time. In the late summer of 1977, that silence settled over Cape Canaveral, Florida, twice within the span of a few weeks. The two Voyager spacecraft, having spent years as bare frames and circuit boards under the fluorescent lights of a clean room, had by now been sealed inside their protective shrouds, mounted atop Titan Centaur rockets, and wheeled out to face the sky they had been built from their very first bolt to leave. Voyager 2 went first, launching on August 20th. Voyager 1, despite its name suggesting otherwise, followed 16 days later on September 5th, its slightly faster trajectory ensuring it would actually overtake its twin and reach Jupiter first. Two departures then, two farewells, each carrying its own particular weight. It is worth pausing here on something that might otherwise pass unnoticed: the strange asymmetry of naming two spacecraft, Voyager 1 and Voyager 2, and having the second one launch first. It says something quietly telling about this mission, that even its numbering was governed not by the order of departure, but by the order of arrival, by where each spacecraft was ultimately headed rather than simply when it left. From nearly the very first moment, these two machines were understood not primarily by their beginnings, but by their destinations. For the engineers and scientists who had spent years bringing these spacecraft into being, watching the final countdown was an experience unlike almost anything else in their professional lives. Many of them had joined the project fresh out of graduate school, young enough that Voyager represented not simply a job, but something closer to a formative chapter of their adult lives. They had spent early mornings and late nights beside these machines, troubleshooting stubborn wiring, rehearsing contingency plans, coaxing reluctant instruments into proper calibration. In a very real sense, they knew these spacecraft more intimately than anyone else alive ever would. And now, in the space of a few final seconds, that intimacy was about to end forever. Picture the control room in those last moments before ignition. Rows of engineers seated at consoles, eyes fixed on readouts, hands resting near controls they would use perhaps once more before their role in this story effectively concluded. There is a particular quality to the quiet in such a room, not tense in the frantic sense often shown in films, but something closer to reverence. Years of work were about to be reduced to a single, irreversible moment, one that would either succeed or fail within the first few violent minutes of the mission, largely beyond anyone's ability to intervene once the engines ignited. Then ignition, a distant thunder rolling out across the Florida coastline, felt in the chest before it is fully heard by the ears. Flame and smoke billowing outward beneath the rocket in vast, roiling clouds, and then, almost impossibly given the sheer scale of machinery involved, the rocket beginning to rise. Slowly at first, as if the ground itself were reluctant to let go, and then with gathering, thunderous speed, climbing into a Florida sky already bright with late summer sun. Within moments, the rocket carrying humanity's small mechanical proxy outward was little more than a bright point of light and a trailing column of smoke, and within a few minutes more, it had vanished entirely from unaided sight, continuing its ascent far beyond where any human eye could follow. For those watching from the ground, particularly those who had spent years of their lives on this project, there is often a strange delay in emotional response to such moments. The mind is occupied in the instant itself with technical vigilance, watching telemetry, listening for confirmation of stage separations, waiting for the reassuring words that indicate the spacecraft has safely reached its intended trajectory. It is only afterward, sometimes hours later, sometimes not until the following day, that the full emotional weight of what has just happened tends to settle in. Many who worked on the Voyager missions have, in later years, described this delayed feeling in strikingly similar terms. A sensation not unlike watching a child leave home for good, not simply moving away for school or for a new job with the reasonable expectation of visits and phone calls and eventual returns, something more permanent than that. A departure with no scheduled return, no assurance of further contact beyond what could be carried on invisible radio waves, and even that only for as long as the growing distance and the spacecraft's own dwindling power allowed. It is a strange kind of parenthood, if it can even be called that, to raise something for years, to know its every mechanism and quirk more intimately than you know most people in your life, and then to release it entirely, understanding from the very outset that this release is permanent, and that whatever it goes on to encounter, whatever wonders or dangers it faces, it will face utterly alone, its only companions the silence of space and its own quietly humming instruments. And yet there was, alongside that ache of separation, something else present in equal measure, something closer to pride, or perhaps something for which the English language does not have a single perfect word, a recognition that this parting, however permanent, was not a loss in the way ordinary losses are understood. It was instead a kind of gift, freely given outward into the universe. These spacecraft were not being sent away out of any lack of love for them. They were being sent away because of it, because everything about their careful design, their redundant systems, their radioactive hearts, their finely tuned instruments, existed specifically to help them survive a journey no human hands could accompany them on. In this sense, the launches of August and September 1977 carried a quality closer to a wedding than a funeral, if such a comparison can be forgiven for its imperfection. A departure celebrated even as it is mourned. A recognition that what is being sent outward carries with it not abandonment, but an entire inheritance. The accumulated knowledge, hope, and care of everyone who built it, folded invisibly into its wiring and its instructions, ready to be unfolded slowly, patiently, across however many years or decades the journey ahead might require. There is a particular image, drawn from the accounts of those present at these launches, worth holding onto for a moment. Engineers who had spent years bent over circuit boards and testing rigs, standing outside now, tracking a bright point of light disappearing into blue sky, some crying openly, some silent, nearly all of them, by their own later accounts, feeling some version of the same strange, mixed emotion. Grief intertwined with hope, loss intertwined with anticipation, the bittersweet sensation of having done everything within their power, and now having no choice but to let go entirely and trust in the work of their own hands. Within the spacecraft themselves, of course, none of this emotional weight registered at all. The instruments continued their careful, automatic sequences, oblivious to sentiment, indifferent to the human hearts that had shaped every circuit within them. Trajectory corrections were calculated, instruments powered on according to their pre-programmed schedules. Communication systems began their long, patient dialogue with Earth, a dialogue that would continue, in one form or another, for decades to come. But for the people standing on the ground, watching two small points of light vanish one after another into the vast Florida sky, September of 1977 marked something that felt, in every meaningful sense, like a true departure. Not simply the technical beginning of a mission, but the emotional beginning of a decades-long vigil, one in which they would continue, from many millions of miles away, to watch over something they loved, unable to reach out and touch it ever again, able only to listen, patiently, for whatever it might have to tell them next. It would not be a long wait before the first of those messages arrived. Within a matter of months, the emptiness surrounding these two small travelers would begin to give way to something entirely new. The first faint signs, gathering slowly on the horizon of their journey, of an enormous, restless giant waiting quietly in the dark ahead. For the first several months after launch, the two Voyager spacecraft traveled through a stretch of space that offered very little to report. This was in many ways the quietest chapter of their entire journey, a long, patient crossing of the emptiness between the inner and outer solar system, far enough from Earth that the novelty of launch had faded, not yet close enough to Jupiter for anything dramatic to begin. For the engineers and scientists back at the Jet Propulsion Laboratory, these were months of steady, unglamorous work, monitoring telemetry, making small trajectory corrections, watching over instruments that for now had very little to actually observe. But distance, however uneventful it may feel in the moment, is not the same as stillness. Every day, whether or not anything appeared to be happening, the two spacecraft were drawing closer to something none of their builders had ever seen up close. Jupiter, the largest planet in our solar system, so massive that it contains more than twice the combined mass of every other planet orbiting the Sun. A world so vast that the Great Red Spot, its most famous feature, a storm swirling endlessly across its surface, could comfortably swallow the entire Earth within its boundaries with room to spare. By early 1979, after roughly a year and a half of largely quiet travel, that patient waiting began to change. As Voyager 1 drew nearer to Jupiter, its cameras began capturing images with steadily improving clarity, and what those images revealed left the scientists watching them in the control room genuinely astonished. It is worth pausing here to understand exactly why. Ground-based telescopes had observed Jupiter for centuries, of course. Astronomers already knew in broad terms what to expect: a massive gas giant banded with colorful cloud formations, orbited by a modest handful of known moons. But there is a profound difference between observing something as a faint, blurred smudge through miles of Earth's own atmosphere and observing it directly, in sharp, close detail, from a vantage point no human being had ever occupied before. It is the difference between reading a detailed description of a place and actually standing within it. As Voyager 1's images grew sharper through January and February of 1979, Jupiter itself began to reveal a personality no telescope had ever fully captured. Its clouds were not simply flat bands of color, as they had often appeared from Earth, but instead roiling, turbulent formations, full of eddies and swirls, storms feeding into storms in patterns of almost hypnotic complexity. The Great Red Spot, long known to exist, now revealed itself as an anticyclonic storm of staggering scale and persistence, its exact mechanisms not fully understood even now, decades later. But it was not Jupiter itself that produced the single most startling discovery of this encounter. It was one of its moons. Before Voyager's arrival, Jupiter's four largest moons, Io, Europa, Ganymede, and Callisto, first observed by Galileo Galilei in 1610, were understood mostly as distant points of light, their surfaces essentially unknown beyond the crudest estimates. Many scientists expected them to resemble Earth's own moon, cold, cratered, geologically dead worlds, their surfaces frozen in place for billions of years, offering little more than a record of ancient impacts. Io shattered that expectation almost immediately. As Voyager 1's cameras turned toward this small, inner moon, an engineer working on navigation, examining one of the returned images not for scientific discovery, but simply to help refine the spacecraft's trajectory calculations, noticed something strange along the edge of Io's disk. A faint, umbrella-shaped plume, rising unmistakably above the moon's surface. At first, there was some hesitation, some careful double-checking, because what that plume appeared to represent seemed almost too extraordinary to be immediately trusted. But the data held, the plume was real, and it meant that this small, distant moon, barely larger than Earth's own, was doing something no one had ever definitively observed anywhere beyond Earth itself. It was volcanically active. The scale of the discovery is worth sitting with for a moment, because it fundamentally rewrote what scientists believed about small, rocky worlds throughout the solar system. Io, it turned out, is the most volcanically active body known to exist, its surface constantly reshaped by eruptions that fling material hundreds of kilometers above the moon's surface, driven not by the kind of internal heat that powers volcanoes on Earth, but by something else entirely. A relentless gravitational tug-of-war between Io, Jupiter, and its neighboring moons, flexing and stretching Io's interior with such force that the friction alone generates enough heat to keep its insides molten. In the control room, as the true nature of what they were seeing became clear, the reaction among scientists was not the composed, clinical satisfaction sometimes associated with scientific discovery. It was something closer to genuine, unguarded joy. Some accounts from that period describe outright disbelief giving way to spontaneous applause, to scientists embracing one another, to a kind of astonished laughter that comes only when reality exceeds even the most optimistic private hopes. No one, going into this encounter, had expected to find an alien world actively erupting before their eyes. It was, by any reasonable measure, one of the greatest surprises in the history of planetary exploration. And Io was only the beginning of what Jupiter's moons had to offer. As Voyager 1 and later Voyager 2 continued their observations, each of the 4 largest Jovian moons revealed its own distinct, unexpected character. Europa, rather than the cratered, ancient surface many had anticipated, showed something startlingly different. A surface remarkably smooth, crossed by long, intricate lines resembling cracks in ice, hinting at the possibility, one that continues to captivate scientists to this day, of a liquid ocean hidden beneath its frozen crust. Ganymede, the largest moon in the entire solar system, larger even than the planet Mercury, revealed a surface of grooved, complex terrain, evidence of geological processes far more active than anyone had expected from a moon so far from the sun's warmth. Callisto, the outermost of the 4, showed a surface heavily scarred by ancient impacts, offering a kind of frozen historical record of collisions stretching back billions of years. Together, these 4 small worlds, previously little more than faint points of light glimpsed through a telescope, suddenly became entire, distinct places, each with its own geology, its own history, its own unresolved mysteries. It was as though a handful of vague rumors had suddenly become detailed, richly illustrated stories, each one deserving of study in its own right. Beyond the moons, Jupiter itself continued to offer new discoveries throughout the encounter. Voyager's instruments detected a faint ring system encircling the planet, invisible from Earth, far more delicate than the famous rings of Saturn, composed of fine dust rather than ice and rock. The spacecraft also measured Jupiter's powerful magnetic field, far stronger than Earth's own, and documented enormous auroras dancing near the planet's poles, driven by the same underlying physics that produces the aurora borealis here on Earth, but on a scale magnified many times over by Jupiter's immense size and power. Through the first months of 1979, first Voyager 1, and then several months later Voyager 2, made their closest approaches to this enormous planet, gathering as much data as their instruments and their limited communication bandwidth would allow, before continuing onward, carried forward by the same gravitational assist that Gary Flandreau had first identified more than a decade earlier. Jupiter's immense gravity, the very force that made this entire mission possible, now bent each spacecraft's trajectory further outward, adding considerable speed to their journey, flinging them toward their next destination with a final, colossal push. For the scientists and engineers who had waited years for this encounter, the Jupiter flybys represented something profound beyond even their considerable scientific value. They were proof, tangible and undeniable, that the entire audacious concept behind this mission actually worked. The spacecraft had survived the journey. Its instruments functioned as designed. And the universe, rather than offering the relatively unremarkable, half-expected confirmation of existing theories, had instead responded with genuine, humbling surprise, revealing an active volcano on a small moon that no one had thought to expect, hinting at hidden oceans, showing rings and auroras and storms of a complexity no ground-based observation could ever have properly captured. It was in every sense a triumphant beginning. But even as the celebrations continued, even as scientists pored over the flood of new images and data, both spacecraft were already moving on, carried by Jupiter's gravity toward a second giant, one that would offer not simply new wonders, but an agonizing choice, one that would ultimately determine the entire future course of Voyager 1's journey. By the time both Voyager spacecraft had left Jupiter behind, something had shifted subtly in how their mission was understood, both by the scientists guiding them from Earth and, in a sense, by the spacecraft's own unfolding story. What had begun as an ambitious but somewhat uncertain venture, a mission that might succeed brilliantly or might falter at its very first major test, had proven itself triumphantly at Jupiter. Now, as both spacecraft continued their long fall towards Saturn, a new set of decisions loomed, decisions that would prove far more difficult and far more consequential than anything the mission had faced before. Saturn had always been the second confirmed destination for both spacecraft, guaranteed by their original approved mission regardless of what happened afterward. But what happened afterward, whether either spacecraft would go on to visit Uranus and Neptune as well, completing something close to the original Grand Tour concept that had inspired the mission in the first place, remained genuinely uncertain. It depended on the spacecraft surviving in good health. It depended on continued funding from a government not always eager to commit money years in advance for missions whose benefits lay so far in the future. And as the spacecraft drew closer to Saturn, it depended on something else entirely: the choices scientists made about how each spacecraft's precious, irreplaceable flyby time would actually be spent. To understand why this became such an agonizing question, it helps to understand what a planetary flyby actually involves. Unlike a spacecraft orbiting a planet, able to observe it patiently over months or years, a flyby mission has only a narrow window, often just a matter of hours during its closest approach, to gather the vast majority of its most valuable data. Every moment of that window is meticulously planned in advance, every camera angle and instrument reading carefully sequenced, because there is no opportunity for a do-over. Once the spacecraft has passed by, it does not circle back. Whatever was captured during that narrow window becomes the entirety of what humanity will ever know from that particular vantage point. This made the trajectory chosen for each spacecraft's closest approach an extraordinarily consequential decision, because a spacecraft's path near a planet cannot serve every purpose equally. The exact route Voyager took past Saturn would determine which of the planet's features it could observe most closely, and crucially, it would also determine the gravitational assist the planet imparted, the bend in trajectory that would either send the spacecraft onward toward Uranus and eventually Neptune, or divert it onto an entirely different path, one that would leave the outer ice giants forever unvisited by that particular spacecraft. And Saturn, it turned out, held a feature that scientists found almost impossible to ignore: its largest moon, Titan. Titan had fascinated astronomers for decades before Voyager's arrival, for one distinctive reason above all others. Unlike nearly every other moon in the solar system, Titan possessed a genuine, substantial atmosphere, thick enough that ground-based telescopes could not see through it to observe the moon's actual surface. This alone made Titan a profound scientific mystery. What kind of atmosphere could a small, distant moon possibly sustain, so far from the warming influence of the sun? What might lie hidden beneath those obscuring clouds? Some scientists speculated about exotic weather systems, methane rain, perhaps even, though this remained deeply uncertain, some remote possibility of conditions relevant to understanding how life might begin. To properly study Titan's atmosphere, however, Voyager 1 would need to fly remarkably close to the moon, threading a precise trajectory that would allow its instruments to analyze the atmosphere's composition and structure in meaningful detail. And here is where the difficult choice emerged, quiet but absolute, embedded in the unforgiving mathematics of orbital mechanics. The particular trajectory that would bring Voyager 1 close enough to properly study Titan was fundamentally incompatible with the trajectory that would allow the spacecraft to continue onward toward Uranus and Neptune using Saturn's gravity. It was not a matter of clever engineering finding some middle path. The physics simply did not allow both. Mission planners were forced to confront a choice that had in truth been implicit in the mission's design from very early on, but which now, with Saturn actually approaching, became urgently, unavoidably real. Voyager 1 could fly close to Titan, gathering data that might answer one of the most tantalizing open questions in planetary science: understanding this strange, atmosphere-shrouded moon that had puzzled astronomers for generations. Or it could forego that close approach, preserving a trajectory that would carry it onward to become the first spacecraft in history to visit Uranus and Neptune, completing something close to the full Grand Tour that had first inspired this entire mission more than a decade earlier. It could not do both, and once the decision was made, it could not be undone. There was no return trip, no correction to be made later, no possibility of reconsidering once new data came in. Whichever path Voyager 1 followed past Saturn would be the only path it would ever have the opportunity to take. The debate among scientists and mission planners over this choice was, by many accounts, genuinely difficult, carrying real emotional as well as scientific weight. Those advocating for the Titan flyby pointed to the moon's unique scientific value, its thick atmosphere unlike anything else observed in the solar system, the tantalizing possibility that understanding its chemistry might illuminate something about the very origins of planetary atmospheres, perhaps even about the conditions that allow life to emerge. This was not a modest scientific curiosity. It was, to many researchers, one of the most compelling mysteries available anywhere in the outer solar system, and an opportunity that might not come again for decades. Those hoping to preserve the trajectory toward Uranus and Neptune, meanwhile, understood that they were arguing for something almost unprecedented. The chance to send a single spacecraft to visit not just 2, but 4 giant planets in a single continuous mission, an achievement that Gary Flandreau's original calculations had first made theoretically possible, but which had never actually been guaranteed as part of Voyager's approved mission. No spacecraft had ever visited Uranus, none had ever visited Neptune. If this particular trajectory were sacrificed for the sake of Titan, the opportunity to reach those distant then only remained with Voyager 2, and there was no certainty Voyager 2 itself would survive long enough or receive sufficient funding to make that extended journey. In the end, the decision fell to Titan. Voyager 1 would be directed onto a trajectory that brought it close enough to properly study the moon's mysterious atmosphere, a choice that meant, definitively and permanently, that it would never visit Uranus or Neptune. Whatever else Voyager 1 accomplished across the remainder of its long journey, and it would go on to accomplish a great deal, its path through the outer solar system effectively ended at Saturn. There is something worth sitting with in this decision, something that reveals a great deal about how scientific exploration actually proceeds, far from the tidy narratives sometimes told after the fact. This was not a mistake or an oversight or a failure of planning. It was a deliberate, carefully reasoned sacrifice made by people who understood exactly what they were giving up and chose to give it up anyway because they believed the mystery of Titan's atmosphere was worth the cost. It reflects a particular kind of scientific integrity, a willingness to pursue the deepest available truth in front of them, even at the expense of a more spectacular, more publicly celebrated achievement that might otherwise have been within reach. When Voyager 1 finally made its close approach to Titan in November of 1980, the data it returned justified, at least scientifically, the difficult choice that had been made. The spacecraft confirmed that Titan's atmosphere was thick, composed primarily of nitrogen, remarkably similar in that one respect to Earth's own atmosphere, though vastly different in nearly every other way, rich in complex organic molecules that hinted at chemistry occurring nowhere else so accessibly in the solar system. It could not see through the thick orange haze to observe Titan's actual surface in detail, a mystery that would remain unsolved for another quarter century, until a different mission, Cassini, and its small companion probe Huygens finally parted those clouds. But it confirmed definitively that this small moon possessed one of the most scientifically compelling atmospheres anywhere within reach of human instruments. Having completed its work at Saturn, Voyager 1's trajectory now curved away from the plane in which the remaining planets orbited, sending it on a path upward and outward, away from any further planetary encounters, toward the empty, uncharted regions beyond. Its exploration of new worlds had ended earlier than it might have, but what it had accomplished, revealing active volcanoes at Jupiter, and now unlocking real, if incomplete, understanding of Titan's strange atmosphere, secured its place regardless as one of the most successful scientific missions in history. Voyager 2, meanwhile, continued along a different path entirely, one that preserved, for now, the far more audacious possibility that had first inspired this entire endeavor. As its twin curved away into a lonely trajectory bound for nowhere in particular, Voyager 2 pressed onward, carrying with it something Voyager 1 no longer possessed: the chance, however uncertain, to become the first spacecraft in history to reach worlds that had never before been visited by anything built by human hands. There's a particular kind of loneliness that belongs only to twins who are separated, a loneliness different in character from any other kind of parting, because it carries within it the ghost of a life that might otherwise have continued running in close, familiar parallel. Human twins separated by distance often describe this feeling, a sense that some part of themselves continues to exist elsewhere, shaped by circumstances and choices they will never fully witness. Voyager 1 and Voyager 2, built side by side from identical blueprints, tested in the same clean rooms, launched within weeks of one another, now found themselves living out a strange mechanical version of this same experience. By the early months of 1981, as Voyager 1 completed its final observations of Saturn and Titan, the spacecraft's trajectory had already begun bending sharply away from the flat, disc-like plane in which the planets orbit the Sun. This upward curve was not an accident, nor was it a compromise forced by some unfortunate miscalculation. It was the direct, inevitable consequence of the gravitational path required to bring the spacecraft close enough to Titan to properly study its atmosphere. Having accepted that trade, mission planners understood exactly where it would lead. Voyager 1 would rise up and out of the solar system's crowded central plane, its path curving away from every remaining planet, carrying it toward regions where nothing but empty space and eventually the thin, tenuous edge of the Sun's influence awaited. For a spacecraft built explicitly to explore, this outcome carried a particular kind of poignancy. Voyager 1 had been present for two of the mission's most spectacular discoveries, the volcanic surprise of Io, the atmospheric mysteries of Titan, but from this point forward it would encounter no more planets, no more moons. No more rings or storms or unexpected discoveries, drawn from a world glimpsed for the very first time. Its remaining journey, however long it might ultimately last, would take it through the emptiness between the outer planets and whatever lay beyond them, a stretch of space so vast and so largely uneventful that decades would pass with little to report beyond the spacecraft's own steady, internal hum of continued operation. Voyager 2's situation could hardly have been more different. Having reached Saturn on a trajectory carefully preserved for exactly this purpose, it now continued onward, still within the flat orbital plane, still aligned with the rare planetary configuration that Gary Flandreau had first identified more than 15 years earlier. Ahead of it, farther than any spacecraft had ever traveled with any planet actually waiting to receive it, lay Uranus, and beyond that, if all continued to go well, Neptune. It is worth pausing on the emotional texture of this divergence, because it reflects something profound about how exploration itself so often unfolds, quietly, without grand ceremony, through a series of small decisions whose full weight only becomes apparent much later. There was no formal farewell exchanged between the two spacecraft, of course. No dramatic final image capturing one twin watching the other depart. The separation occurred exactly as everything else in this mission occurred, through the patient, indifferent unfolding of orbital mechanics, through trajectories calculated years in advance, executed now with a kind of quiet, mathematical inevitability that no sentiment could alter. And yet, for the human beings following this mission from Earth, the moment carried real emotional resonance. Engineers and scientists who had worked with both spacecraft, often for years, understood clearly that the mission had now permanently forked into two distinct stories. One spacecraft, having made its sacrifice at Saturn, would spend the remainder of its operational life in a kind of prolonged solitary passage, its scientific contributions largely concluded, its ongoing significance shifting gradually from planetary explorer to something else entirely, an increasingly solitary emissary of humanity, carrying its instruments and its golden record ever outward into regions no spacecraft, and eventually no human construction of any kind, had ever occupied before. The other spacecraft, meanwhile, would carry forward the dream that had first animated the entire mission, the audacious hope of visiting all 4 giant planets in a single continuous journey. For the scientists who had fought hardest to preserve this trajectory during the difficult decisions at Saturn, watching Voyager 2 continue onward, uninterrupted, must have carried its own particular satisfaction, tempered by the knowledge of just how much still remained uncertain. Uranus and Neptune lay years away yet, and years bring their own risks. Equipment failures, funding shortfalls, unexpected hazards that no amount of careful planning could fully anticipate. There is something worth understanding here about the peculiar psychology of long-duration space missions, one that distinguishes them sharply from almost any other human endeavor. In most fields of exploration throughout history, the moment of departure and the moment of discovery lie relatively close together, separated by weeks or months, occasionally years, but rarely by the better part of a decade. Voyager 2's journey toward Uranus would require roughly 4 additional years beyond Saturn, and its subsequent journey toward Neptune a further 3 years beyond that. This meant that the scientists and engineers who had fought for this trajectory in 1980 would need to sustain their attention, their expertise, and quite often their careers, across a span of time long enough for entire technological eras to shift beneath them. Consider what those intervening years actually contained elsewhere on Earth, while Voyager 2 continued its long, quiet crossing toward Uranus. Personal computers moved from a curiosity into ordinary households. An entirely new generation of engineers graduated from universities that had barely begun teaching about spacecraft when Voyager first launched. The scientists who had assembled these spacecraft as young graduates in the 1970s were now, by the mid-1980s, senior figures in their fields, watching younger colleagues join a mission that had, by this point, already run longer than many of those colleagues' entire careers up to that moment. And yet, throughout all of this, Voyager 2 continued its silent, patient crossing, largely unaffected by the passage of terrestrial time. Its instruments required no updates from Earth to continue functioning. Its trajectory needed only occasional, minor corrections. In a sense, the spacecraft itself existed in a kind of suspended present tense, indifferent to the accelerating pace of change happening millions of miles behind it, focused entirely on the singular, unchanging task embedded in its original programming. Continue outward, gather what can be gathered, and transmit faithfully back toward a home that grew, with every passing day, a little more distant and a little more different from the world that had first sent it on its way. Meanwhile, Voyager 1, having completed its planetary encounters, entered a phase of its mission that would define much of its remaining existence. A long, uneventful passage through increasingly empty space, its scientific instruments now focused less on dramatic new discoveries and more on the subtler, quieter work of characterizing the space between the planets and eventually, the very edge of the sun's influence itself. This was, in its own way, no less scientifically valuable than the earlier planetary encounters, though it lacked their immediate visual drama. There would be no more volcanic plumes to photograph, no more mysterious hazy atmospheres to analyze. Instead, Voyager 1's instruments would spend years quietly measuring the faint, diffuse particles and magnetic fields that fill the vast spaces between worlds, slowly building a picture of an environment far subtler, and in some ways far stranger than anything a camera alone could capture. It would be easy, looking back on this period, to think of Voyager 1's remaining journey as somehow lesser, a kind of extended epilogue following the more dramatic achievements of its earlier years. But this framing misses something important about what this mission had always represented. From its very inception, Voyager was never simply about photographing planets, however spectacular those photographs turned out to be. It was about extending human perception and understanding into regions our bodies could never directly experience, about building instruments patient enough and durable enough to keep listening and measuring and reporting back long after the more immediately spectacular phases of discovery had concluded. By these measures, Voyager 1's quiet, uneventful passage through the years following Saturn was not a diminishment of its purpose, but a continuation of it, carried out in a different key. Its instruments continued working. Its radioactive heart continued its slow, steady decay, generating just enough power to keep its systems alive. And its distance from Earth continued to grow, day by day, mile by patient mile, carrying it steadily toward a threshold that no human-made object had ever crossed before, though that threshold itself remained, for now, still many years away. Voyager 2, for its part, continued its own long approach toward Uranus, carrying forward not just its instruments and its golden record, but something closer to a shared aspiration, held quietly by everyone who understood exactly what would be required to reach not just one, but two entirely unvisited worlds. The years ahead would test the spacecraft's endurance and the patience of everyone still watching over it from Earth. But if it succeeded, it would accomplish something no other mission, before or since, has ever managed. A single continuous voyage through the realm of all four giant planets, culminating at the very edge of what the sun's light could meaningfully reach. That distant, icy edge, still years away, was where Voyager 2's story would next unfold. Distance changes the meaning of things. A journey of a few 100 million miles, once considered the very edge of practical exploration, comes to feel almost intimate once a spacecraft has already traveled several billion. By the middle of the 1980s, as Voyager 2 continued its long approach toward Uranus, the mission itself had entered a kind of territory, both physical and psychological, that its original planners could describe only in careful projections and hopeful estimates. No spacecraft had ever traveled this far with a planet still waiting to receive it. Everything about to happen would be, in the truest sense, unprecedented. Uranus itself had long occupied an unusual place in the public imagination, even among those who followed astronomy closely. Discovered in 1781 by William Herschel, it held the distinction of being the first planet identified using a telescope, rather than through observation with the naked eye alone, as the 5 inner and outer planets visible from Earth had been known since antiquity. And yet, despite this distinguished place in the history of astronomy, Uranus had remained, in the 2 centuries since its discovery, almost entirely mysterious. Ground-based telescopes, even the most powerful available by the 1980s, could resolve little more than a faint, featureless disk, a pale blue-green orb offering almost no visible detail, no discernible weather patterns, nothing resembling the dramatic swirling clouds so easily photographed on Jupiter and Saturn. This near-total absence of visible detail led some scientists, in the years before Voyager's arrival, to suspect that Uranus might simply be a quieter world than its larger siblings, its atmosphere calmer, its internal dynamics less dramatic. Others suspected this apparent calm was simply an illusion created by distance and the limitations of Earth-based instruments, masking activity that closer observation might yet reveal. Only a spacecraft, flying directly past the planet at close range, could resolve which of these expectations, if either, was correct. Voyager 2 made its closest approach to Uranus on January 24, 1986, a date that had been anticipated by mission scientists for years, and prepared for with a precision built on more than 8 years of continuous spacecraft operation. By this point, the spacecraft itself had aged considerably in engineering terms, its instruments having operated far longer than their original design specifications had strictly guaranteed, its onboard computer systems representing technology that, by the standards of 1986, already felt like a relic of an earlier decade. And yet everything still worked, a testament to the almost obsessive redundancy and care that had gone into its original construction nearly a decade earlier. What Voyager 2 revealed about Uranus as it approached and eventually passed the planet confirmed some expectations while overturning others in ways that scientists found genuinely puzzling. The planet's atmosphere, it turned out, truly was remarkably calm compared to Jupiter and Saturn, its cloud patterns faint and subtle, requiring significant image processing simply to become visible at all. This relative quiet was not, however, boring in any scientific sense. It raised its own compelling questions about why a planet this size and this cold would exhibit so little of the dramatic weather seen on its larger neighbors, questions that scientists continue to investigate using more recent, more powerful telescopes even today. Far stranger than the planet's calm atmosphere, however, was something Voyager's instruments revealed about Uranus's fundamental orientation in space. Every other planet in the solar system rotates on an axis that stands, roughly speaking, upright relative to its orbital path around the Sun, tilted at various modest angles, but broadly aligned in a manner one might expect. Uranus does not follow this pattern at all. Its axis of rotation is tilted so dramatically, more than 90 degrees from what would be considered typical, that the planet essentially rotates on its side, rolling around the Sun rather than spinning upright like a top. This meant that during Voyager's flyby, one of the planet's poles happened to be pointed almost directly at the approaching spacecraft, presenting scientists with an almost bewildering observational puzzle, a world whose entire relationship to sunlight and seasons operates unlike anything else in the solar system. The cause of this extreme tilt remains, even now, a subject of scientific investigation rather than settled certainty, though the leading explanation involves a massive collision early in the solar system's history between the forming planet and another large body, a violent encounter that would have knocked Uranus onto its side permanently, leaving behind an axis tilt that has persisted for billions of years since. Beyond the planet itself, Voyager 2's flyby of Uranus yielded a wealth of new information about its surrounding moons and rings. Prior to this encounter, only 5 moons of Uranus were known, all relatively large and identified through Earth-based telescopic observation over the preceding 2 centuries. Voyager's cameras, capable of detecting far fainter and smaller objects than any ground-based instrument, discovered 10 additional moons during this single flyby, small, dark bodies previously entirely unknown, expanding scientific understanding of just how crowded and complex this distant planetary system truly was. Among the previously known moons, one in particular captured the attention of scientists in ways no one had fully anticipated. Miranda, one of the smaller of Uranus's major moons, revealed a surface unlike anything observed elsewhere in the solar system up to that point. A chaotic patchwork of wildly varying terrain, deep canyons sitting adjacent to smooth plains, jumbled ridges cutting across older, heavily cratered regions in patterns that seemed almost geologically incoherent. Some scientists speculated that Miranda might once have been shattered by a massive impact and subsequently reassembled by its own gravity, its jumbled surface representing the scars of that ancient violence, though this remains, like so much about the outer solar system, an area of ongoing scientific interest rather than settled fact. Having completed its historic flyby of Uranus, Voyager 2 continued onward, carried by the planet's gravity toward its final, and in many ways most significant planetary destination. Neptune lay still more than 3 years ahead, a journey that would carry the spacecraft even further from the warmth and light of the Sun, into a region of the solar system so distant and so poorly understood that even basic questions about Neptune's fundamental characteristics remained genuinely uncertain heading into the encounter. By the time Voyager 2 finally reached Neptune, in August of 1989, the spacecraft had been operating continuously for exactly 12 years, an extraordinary span for a mission that had, at its original approval, been formally guaranteed only through the Saturn encounter nearly a decade earlier. Every additional year, every additional planetary visit beyond that original commitment represented not simply a scientific achievement, but a triumph of engineering endurance, a testament to just how thoroughly those early designers had anticipated the challenges of operating so far, for so long, without any possibility of repair or adjustment. Neptune itself, when Voyager 2 finally arrived, proved to be a world of striking, unexpected vibrancy. Unlike the relatively calm, muted atmosphere observed at Uranus, Neptune displayed genuine, dynamic weather, its deep blue atmosphere marked by visible storm systems, including a large, dark oval feature that scientists came to call the Great Dark Spot, a storm system bearing a striking resemblance, in general character if not in exact mechanism, to Jupiter's own Great Red Spot. This was, in itself, a genuine surprise. Neptune receives barely half the sunlight that reaches Uranus, and roughly 900 times less than what warms the Earth, and yet its atmosphere displayed some of the fastest wind speeds ever recorded anywhere in the solar system, powerful jet streams whipping across its surface at speeds exceeding 1,500 miles per hour. A puzzle that continues to intrigue atmospheric scientists studying how a planet so distant and so cold could sustain such ferocious internal weather. Neptune's largest moon, Triton, offered its own remarkable discovery. Unlike nearly every other large moon in the solar system, Triton orbits its planet in a retrograde direction, opposite to the direction of Neptune's own rotation, a strong indication that Triton was not originally formed alongside Neptune at all, but was instead captured later, likely a wandering object drawn in from the distant, icy reaches of the solar system. Voyager's images revealed Triton to be an actively geological world as well, its surface marked by what scientists identified as evidence of cryovolcanism, eruptions not of molten rock, as on Earth, but of extremely cold material, nitrogen ice and slush, venting outward from beneath Triton's frozen surface in dark, streaking plumes. With its flyby of Neptune complete, Voyager 2 had accomplished something no other spacecraft before or since has ever managed. It had visited in a single continuous mission all 4 giant planets of the outer solar system, becoming the first and to this day, the only spacecraft to have observed Uranus and Neptune directly. The audacious dream first identified in Gary Flandreau's orbital calculations more than 2 decades earlier, the rare alignment that would not recur for another century and a half, had been fully and completely realized. And yet, even as this extraordinary chapter of exploration concluded, both spacecraft, Voyager 1 far ahead in the emptiness beyond Saturn, Voyager 2 now departing Neptune on its own outward trajectory, continued moving forward, carried by momentum and gravity into a phase of the mission that none of their original planners had been able to fully guarantee. Their primary mission, the exploration of the outer planets, was now complete. What remained was something else entirely, the quiet, uncertain question of what these 2 spacecraft might still accomplish once there were no more planets left to visit at all. By the close of the 1980s, both Voyager spacecraft had, in the most literal sense, finished the job they were originally sent to do. Voyager 1 had completed its studies of Jupiter and Saturn years earlier, its trajectory long since carrying it away from any further planetary encounters. Voyager 2 had just accomplished something even its most optimistic designers had hardly dared promise at the outset, becoming the only spacecraft in history to visit all 4 giant planets of the outer solar system. By any reasonable measure, the mission had already succeeded beyond what anyone connected to its difficult early years, its funding battles, its razor-thin margins for error, could have confidently expected. And yet, within the scientific community surrounding the mission, a quiet, persistent idea had been circulating for some time, one that had little to do with any planet, moon, or ring system. It concerned, instead, a single photograph, one unlike anything either spacecraft had been designed or instructed to take. The person most closely associated with this idea was Carl Sagan, an astronomer and one of the most recognizable public voices in American science during this period. Known for his ability to translate complex scientific concepts into language that captured the imagination of ordinary people far beyond the walls of any research institution. Sagan had been involved with the Voyager mission from its earliest years, playing a central role, in fact, in curating the contents of the golden record carried aboard each spacecraft. But the idea he now proposed was, in its own way, a strange counterpart to that earlier work. Rather than sending a message outward describing who we are, he wanted the spacecraft to turn briefly around and show us something about where we actually stood. Specifically, Sagan proposed that before Voyager 1's cameras were permanently powered down, a step that mission engineers had already begun planning in order to conserve the spacecraft's limited remaining electricity for other instruments, the spacecraft should be commanded to turn its camera back toward the inner solar system and take a series of photographs. Not photographs of any particular planet in scientific detail, but a wide, sweeping portrait capturing several planets simultaneously, including, crucially, one small, pale point representing Earth itself, viewed from a distance far greater than any human eye or any previous photograph had ever captured it from. This request, though it might sound straightforward, was met initially with genuine reluctance among some members of the mission team, for reasons that were entirely practical rather than philosophical. By this point, Voyager 1 was operating at a distance where sunlight had grown extraordinarily faint, meaning that pointing its cameras anywhere near the direction of the sun risked flooding its sensitive imaging equipment with scattered light, potentially damaging instruments that could not be repaired or replaced. There was also the simple matter of scientific value in the narrowest sense. From a purely data-driven perspective, a photograph showing Earth as nothing more than a few scattered pixels against the vast darkness offered essentially no new scientific information about our planet. Every measurable fact about Earth's atmosphere, its size, its composition, was already known in far greater detail through observation from Earth itself. Sagan understood these objections fully, and he did not dispute their technical validity. His argument for the photograph rested on a different kind of value entirely, one not easily quantified in the language of data points and spectral analysis, but no less significant for that. He believed and argued this case patiently and persistently to those responsible for the mission's final decisions, that there was something profoundly important about actually seeing our own world from such an extraordinary distance, something that no amount of abstract scientific knowledge about Earth's size or position could substitute for. Human beings, he suggested, are shaped as much by images and perspective as by data and fact. A photograph capturing Earth as a single, vulnerable point of light lost among the vastness of space might accomplish something no scientific paper ever could, a shift, however small, in how people understood their own place within the universe. This argument ultimately prevailed. In February of 1990, after Voyager 1 had traveled roughly 4 billion miles from the Sun, well beyond the orbit of Neptune, its cameras were carefully commanded to turn back toward the inner solar system one final time, capturing a series of 60 images across several of the solar system's planets, an assembly that would eventually become known collectively as the family portrait. The technical execution of this request was, in its own right, a remarkable feat of precision engineering, executed across a distance so vast that sending a single command and receiving confirmation of its execution required more than 5 hours simply for the radio signal to make the round trip. Every angle, every exposure setting had to be calculated with exacting care, accounting for the spacecraft's exact position, the precise locations of each target planet, and the specific risks posed by any stray sunlight that might inadvertently enter the camera's field of view. There was no opportunity to review the images and make adjustments if something went wrong. The entire sequence had to succeed on essentially the first attempt, executed automatically according to instructions transmitted from a control room on a planet now smaller and fainter than most of the stars surrounding it in the spacecraft's own field of view. The images that eventually made their way back to Earth, arriving after their own multi-hour journey across the solar system, captured 6 of the solar system's planets: Venus, Earth, Jupiter, Saturn, Uranus, and Neptune, each rendered as little more than a small point or crescent of light against an overwhelming backdrop of darkness. Mercury proved too close to the sun's glare to be safely photographed, and Mars, at the particular moment of the imaging sequence, was positioned in a way that made capturing it impractical. Even accounting for these limitations, the resulting collection of images represented something entirely unprecedented in human history. A single vantage point from which nearly the entire known architecture of our solar system, our home in the truest sense, could be observed together, however faintly, in one continuous perspective. Among these images, one in particular would go on to hold a significance far beyond what its modest visual content might initially suggest. Within a narrow band of scattered light, a kind of accidental artifact created by sunlight refracting through the camera's own internal optics, sat a single pale, bluish dot, barely a single pixel wide, suspended within that stray beam of light almost as though caught, quite literally, in a passing sunbeam. This was Earth, not merely represented in the image or symbolized by it, but genuinely, physically present within it, its actual reflected light, having traveled the full 4 billion miles from our planet to the spacecraft's camera, captured directly onto the imaging sensor. Every person who had ever lived, every home that had ever stood, every ocean, every mountain range, every fragile, complicated human story ever told, existed somewhere within that single, barely visible point of light. At the time this image was captured and transmitted, its full emotional and philosophical significance was not yet widely appreciated, even among many members of the mission team themselves. It existed initially as simply one frame within a larger technical sequence, notable perhaps for its novelty, but not immediately recognized as something that would come to occupy such a distinctive place in how people throughout the world thought about their own planet's position within the cosmos. That recognition would take a little more time to fully develop, shaped significantly by the words Carl Sagan himself would eventually write about this particular photograph. Reflections that moved well beyond the technical details of the image's capture into something closer to philosophy, or perhaps something closer still to a kind of secular meditation on humility, unity, and the strange, humbling scale of our actual place in the universe. Before turning to those words, though, and to everything they eventually came to mean for how millions of people understood this photograph, it is worth simply sitting for a moment with the image itself. A single beam of scattered sunlight crossing an otherwise empty photograph taken from 4 billion miles away. And somewhere within that narrow band of accidental light, smaller than a single grain of sand held at arm's length, everything we have ever known. There is a particular kind of silence that follows a photograph like this one, a silence different from mere quiet, closer to the pause that settles over a room after someone has said something too large, too true, to immediately respond to. When the image finally reached wider audiences beyond the immediate circle of mission scientists, it did not arrive with fanfare or dramatic announcement. It arrived quietly, almost humbly, a small, grainy photograph among many other images returned by Voyager 1 during its final act as an active observer of the solar system. Its true significance would take shape gradually, not through the image alone, but through the words eventually written about it. Carl Sagan had championed this photograph for reasons that went beyond scientific curiosity, and in the years following its capture, he articulated those reasons in a passage that would become, in time, one of the most quoted and reflected upon pieces of writing about humanity's place in the cosmos. He described the pale dot as our home, understanding in that description everything the image did and did not contain, every person we have ever loved or lost, every triumph and every tragedy across the entire span of recorded history. Every war fought over some small fraction of that single pixel's surface, every border drawn and redrawn, every flag planted with such fierce, momentary conviction. All of it contained within a point of light so small that without careful attention, an observer might easily overlook it entirely, lost within the surrounding grain of the photograph itself. There is something quietly devastating in this realization, and something quietly clarifying as well, two responses that might initially seem to pull in opposite directions, but which, upon reflection, turn out to be more closely related than they first appear. The devastating part lies in the sheer scale of insignificance the image reveals, the recognition that everything we consider vast and consequential in our daily lives, our cities, our nations, our conflicts, our achievements, occupies a physical space so small that it cannot even be resolved into more than a single scattered point of light. When viewed from a distance, our own spacecraft had by this point already traveled far beyond. And yet this same recognition carries within it something closer to comfort, or perhaps closer to perspective than to despair. Because if every human conflict, every act of cruelty, every moment of division that has ever divided one group of people from another has occurred entirely within this single, tiny point of light, then those divisions themselves become, in some sense, difficult to sustain with quite the same intensity once genuinely understood at this scale. Sagan wrote, in reflecting on the image, of how difficult it becomes to take seriously the notion of privileged position, The idea that any particular nation, any particular ideology, any particular corner of this small world holds some special, elevated claim over the rest, when the entire stage on which all of that supposed importance plays out amounts to little more than a mote of dust, suspended in a beam of accidental sunlight. This is not, it should be said clearly, an argument that human lives, human choices, or human history lack meaning. Quite the opposite. The smallness revealed by the photograph does not diminish the significance of what happens within that small space so much as it reframes the context in which that significance exists. Every act of kindness, every scientific discovery, every piece of art or music or literature ever created, all of it happened here, on this single, fragile point of light, with no external audience, no cosmic witness beyond whatever meaning we ourselves choose to assign it. There is no other place, as far as any instrument has yet discovered, where any of this has happened at all. That absence of any confirmed company throughout the vast surrounding darkness makes what exists here, however small, feel not less precious, but considerably more so. This particular tension between cosmic insignificance and profound preciousness sits at the very heart of why this photograph resonated so deeply with so many people who encountered it, often for the first time, through Sagan's own writing and public reflections. It offered a way of understanding humanity's situation that avoided two equally tempting but equally distorting extremes. On one side lies a kind of exaggerated self-importance, the assumption, whether stated explicitly or simply absorbed unconsciously through the ordinary business of daily life, that human affairs occupy some central, privileged position within the broader universe. On the other side lies something closer to nihilism, the conclusion that if we are truly this small, truly this insignificant on any cosmic scale, then perhaps nothing we do actually matters at all. The pale blue dot offers a quieter alternative to both of these positions. It suggests, without demanding, that our significance was never meant to be measured against the vastness of the universe in the first place. We do not need to be large or central or cosmically consequential in order for what happens here to matter enormously to us, the only beings, as far as we currently know, capable of caring about it at all. In a universe apparently indifferent to meaning, we appear to be, at least within the small circle of our current knowledge, the only ones providing any. There is also, within this photograph and the reflections it inspired, a particular argument for a kind of unity that transcends the ordinary divisions of human life. If every conflict humanity has ever fought, every border dispute, every war over ideology or resources or territory, occurred entirely within the confines of this single, barely visible point of light, then the differences that have so often felt from within human experience like vast, unbridgeable chasms begin to look, from this distance, considerably smaller than they once seemed. Not unimportant, perhaps, but certainly less absolute, less deserving of the fierce, sometimes violent convictions so often invested in them. It would be naive, of course, to suggest that a single photograph, however profound its implications, has the power to resolve human conflict or dissolve the genuine, complicated differences that continue to divide people across the world. The pale blue dot did not end war, did not eliminate injustice, did not somehow persuade humanity to set aside its disagreements in light of newfound cosmic perspective. But it did offer something valuable nonetheless, a tool for perspective available to anyone willing to genuinely sit with what the image represents, a reminder always available should anyone choose to seek it out, of just how much all of us ultimately share, simply by virtue of existing together on this same small, fragile point of light, with nowhere else, at least for now, to call home. For the scientists and engineers who had spent years of their lives working on this mission, the pale blue dot photograph came to represent something rather different from, though not unrelated to, its broader philosophical resonance. It served as a kind of quiet culmination, a final act performed by a spacecraft that had already accomplished so much in terms of pure scientific discovery, offering now something closer to a gift, one final image capturing not some distant, alien world, but the very world that had sent it on its journey in the first place. There was a certain symmetry in this, a spacecraft built by human hands, carrying human curiosity outward across billions of miles, turning back one final time not to study some distant giant planet, but to offer humanity a chance to see itself clearly, for perhaps the first time, from a perspective that had never before been available to any person throughout the entire span of human history. After this photograph was captured and transmitted, Voyager 1's cameras were, as planned, powered down permanently, a deliberate decision made to conserve the spacecraft's steadily dwindling power for other instruments considered more valuable for the mission's continuing scientific goals. This meant that the pale blue dot, this single, humble image of a scattered point of light within a stray beam of sunlight, would remain the very last photograph Voyager 1 would ever take. Its long career as a visual explorer, one that had begun with the volcanic surprises of Io more than a decade earlier, concluded here, with this quiet, unassuming portrait of home. What remained ahead for both spacecraft was a mission unlike anything either had been originally designed to fully anticipate. No further images to capture, no further worlds to visually explore. Only the continuing outward journey itself, carrying each spacecraft steadily closer to a boundary far stranger and more elusive than any planet or moon, the very edge of the sun's own vast, invisible influence, a frontier that would soon become the next great and considerably more abstract chapter in this remarkable mission's ongoing story. There is a particular kind of frontier that resists easy description, not because it lacks significance, but because it possesses no fixed location, no visible marker, nothing resembling the clear, definite boundaries that separate countries on a map or planets within their orbits. For years following the completion of both Voyager spacecraft's planetary encounters, scientists understood that somewhere ahead of them, at a distance that could only be estimated rather than precisely known in advance, lay exactly this kind of frontier. The edge of the sun's own influence, the boundary where the solar wind, that constant stream of charged particles flowing outward from our star, finally surrenders to the pressure of the vast, largely empty space between the stars themselves. This boundary carries a formal name, one that sounds, appropriately enough, almost otherworldly in its own right, the heliopause. Understanding what this boundary actually represents requires setting aside, for a moment, the more familiar image of the solar system as a fixed collection of planets orbiting within empty space. In reality, the sun does not simply sit at the center of an inert system, its influence limited neatly to the orbits of its planets. It continuously exhales, in a sense, a steady outward stream of charged particles, electrons and protons, moving outward in every direction at speeds reaching well over 1,000,000 miles per hour. This solar wind creates around our entire solar system something like an enormous, invisible bubble, a region of space dominated by our own star's particles and magnetic field, extending vastly beyond the orbit of even the outermost planet. But this bubble, however vast, is not infinite. Eventually, the outward pressure of the solar wind weakens enough that it can no longer overcome the faint, but persistent, pressure of the interstellar medium, the extremely thin scattering of particles and magnetic fields that exists in the space between different star systems throughout our galaxy. Where these two pressures finally reach equilibrium, where the sun's own particles give way to this broader galactic environment, lies the heliopause, the true, functional edge of our solar system in the most physically meaningful sense, a boundary considerably farther out than the orbit of any planet, farther even than the icy, distant world of Pluto. For years, as both spacecraft continued their outward journeys following their planetary encounters, scientists could only estimate roughly where this boundary might actually lie, based on theoretical models of solar wind pressure and indirect measurements taken from Earth and from other spacecraft positioned closer to home. No human-made object had ever traveled far enough to measure the heliopause directly, which meant that as Voyager 1 and eventually Voyager 2 continued their patient, unglamorous journey through the increasingly sparse outer reaches of the solar system, they were, in effect, conducting one of the longest and most delicately anticipated experiments in the history of space exploration, an experiment whose successful conclusion could not be scheduled or predicted with any real precision, but only patiently awaited. This period of the mission, stretching across many years following the conclusion of both spacecraft's planetary encounters, represented something genuinely unusual within the broader history of space exploration. There were no dramatic new images to capture, no previously unseen worlds revealing themselves in unexpected detail. Instead, both spacecraft settled into a much quieter, more subtle kind of scientific work, continuously monitoring the characteristics of the solar wind surrounding them, its density, its speed, its magnetic properties, searching for the gradual, sometimes ambiguous signs that might indicate the approaching boundary. This search required a particular kind of patience, both from the spacecraft's instruments and from the scientists interpreting their data back on Earth. The heliopause does not announce itself with any single, dramatic signal. Its approach reveals itself instead through a gradual accumulation of subtler changes, a slow thinning of solar wind particles, fluctuations in magnetic field strength, an increasing frequency of a particular kind of charged particle originating not from the sun at all, but from sources far beyond it, out among the distant stars of our own galaxy. Distinguishing genuine signs of an approaching boundary from ordinary background fluctuations required years of careful, incremental analysis, a scientific puzzle assembled slowly, one small data point at a time, across a period of study far longer than most entire scientific careers. Voyager 1, having traveled outward on its steep trajectory since departing Saturn decades earlier, reached this elusive boundary first. In August of 2012, more than 35 years after its original launch, instruments aboard the spacecraft detected a series of changes that, after careful analysis extending across several additional months, scientists confirmed represented the spacecraft's crossing into interstellar space. Voyager 1 had left the heliosphere, the sun's own protective bubble, entirely, becoming the first human-made object in history to travel beyond the direct influence of our own star and into the broader, largely unexplored medium that fills the space between stars throughout our galaxy. It is worth taking a moment to fully appreciate the scale of what this achievement actually represents, because its true magnitude can be easy to underestimate simply through the abstract, technical language typically used to describe it. Every previous human journey, every previous human-made object, however far it may have traveled, remained fundamentally within the sun's domain, still influenced in ways subtle or obvious by our own star's particles and magnetic field. Voyager 1's crossing of the heliopause represented something categorically different, the first genuine departure from the entire physical system that has surrounded and shaped human existence since long before any human being ever looked up and wondered what lay beyond the visible sky. The confirmation of this crossing did not arrive as a single, dramatic moment, precisely because the boundary itself does not present itself with any such clean, unambiguous signal. Instead, scientists spent months carefully analyzing the accumulated data, examining changes in the density of surrounding particles, changes in the character of the magnetic field surrounding the spacecraft, before finally announcing, with appropriate scientific caution, that Voyager 1 had indeed crossed into interstellar space. This measured, careful process of confirmation stands in quiet contrast to the instantaneous drama one might expect from popular depictions of similar milestones, a reminder that even the most profound achievements in space exploration often unfold not through sudden revelation, but through patient, careful accumulation of evidence. For the scientists who had devoted decades of their careers to this mission, many of them now considerably older than when they had first begun working with these spacecraft as young researchers in the 1970s, this moment carried a particular, hard-won significance. It represented the successful conclusion of a scientific question that had remained genuinely open for the entire duration of their careers, a question about the fundamental size and shape of our own solar system's boundary with the broader galaxy, finally answered not through theoretical calculation alone, but through direct physical measurement carried out by an instrument some of them had personally helped design and build many years earlier in circumstances that felt by this point almost impossibly distant. Voyager 2, traveling along its own separate trajectory since departing Neptune decades earlier, would eventually reach and cross this same boundary as well, though not until several years later, in November of 2018, adding a second, independent confirmation of humanity's crossing into interstellar space, gathered from a somewhat different location and trajectory than its twin. Providing scientists with valuable comparative data about the actual shape and characteristics of this elusive boundary, which, it turned out, was neither perfectly spherical nor entirely uniform in its properties across different directions. Having crossed this threshold, both spacecraft now occupied a genuinely unprecedented position, no longer explorers of our own solar system in any conventional sense, but rather humanity's first true emissaries into the broader galactic environment beyond it. This did not mean, it is worth clarifying, that either spacecraft had somehow left the solar system entirely in every meaningful sense. The sun's gravitational influence, distinct from the solar wind that defines the heliopause, continues to extend vastly farther still, out to the distant, sparse region of icy bodies known as the Oort cloud, a journey that would require many thousands of additional years for either spacecraft to complete, far beyond any reasonable expectation for their continued operation. But in terms of the specific physical boundary defined by the sun's outward stream of particles, both spacecraft had genuinely, definitively moved beyond it. This achievement, remarkable as it was, arrived alongside a quieter, more sobering reality that mission scientists had long understood was approaching regardless of when or whether either spacecraft successfully crossed the heliopause. Both Voyagers were growing old, in the specific, unforgiving way that spacecraft age, not through wrinkles or gray hair, but through the slow, irreversible decline of their onboard radioactive power source, the same plutonium heart that had faithfully sustained their instruments across 4 decades of continuous operation, now producing steadily less electricity with each passing year, an inevitable consequence of the same physical decay process that had made it useful as a power source in the first place. This meant that even as both spacecraft achieved one of the most significant milestones in the entire history of space exploration, becoming the first human-made objects to reach true interstellar space, they were simultaneously approaching an entirely different kind of threshold, one considerably less triumphant, though no less inevitable. The question was no longer whether these remarkable machines could reach the edge of the solar system. They had already answered that question decisively for both spacecraft, beyond any reasonable doubt. The question now was how much longer their steadily fading power might allow them to continue functioning at all, and what exactly that slow, unavoidable decline would actually look like for instruments that had operated so faithfully, for so long, so impossibly far from any hand that might reach out to help them. There is a particular kind of decline that belongs to machines built to last far beyond their original expectations, one quite different from the sudden failure of a device that simply breaks. It is a decline measured not in moments, but in years, sometimes decades, a gradual, almost imperceptible loss that becomes visible only when compared against distant points in the past, the way a person might notice how much has changed only after looking back at a photograph taken many years earlier. This is the kind of decline that has, for some time now, been quietly unfolding aboard both Voyager spacecraft, a slow fade written not in any single dramatic failure, but in the patient, unstoppable arithmetic of radioactive decay. To understand this decline properly, it helps to return to the source of power that has sustained both spacecraft since the very earliest days of their mission, decades ago. Each Voyager carries a small quantity of plutonium-238, contained within a device known as a radioisotope thermoelectric generator, a technology that converts the natural heat produced by radioactive decay into a steady, reliable supply of electricity. This system has no moving parts to wear out, no fuel that needs replenishing, no maintenance of any kind required across the entire span of the mission. In this sense, it represents one of the most elegantly durable technologies ever placed aboard a spacecraft, precisely suited to a mission that would travel so far beyond any possibility of repair. But durability in this particular context does not mean permanence. Plutonium-238 decays according to a fixed, entirely predictable physical process, its radioactivity, and therefore its heat output, diminishing steadily over time according to what physicists call its half-life, the span of time required for half of any given quantity of the material to decay into other substances. For plutonium-238, this half-life is approximately 88 years, meaning that the power available to each Voyager spacecraft has been declining, slowly but with complete mathematical certainty, since the very moment its radioactive fuel was first manufactured, long before either spacecraft ever left the ground. This decline is not the kind of dramatic countdown often depicted in popular stories about spacecraft running out of power, some sudden, climactic moment when the lights simply go out all at once. It is instead something closer to a long, gradual dimming, a few percentage points of available power lost with each passing year, so gradual that no single year brings any crisis on its own, and yet so relentless that across the span of decades, its cumulative effect becomes impossible to ignore. By the time both spacecraft had crossed the heliopause and entered true interstellar space, mission engineers back on Earth found themselves facing a particular kind of ongoing decision, one that would recur with increasing frequency as the years continued to pass. Each spacecraft's declining power supply meant that, sooner or later, there would no longer be enough electricity available to run every onboard instrument simultaneously. Something would eventually have to be turned off. And once turned off, given the extreme cold that instrument would then be exposed to, without the benefit of its own internal heating systems, there was a strong likelihood that it could never be safely turned back on again. This created a very particular kind of ongoing responsibility for the engineers managing both missions, one quite unlike the earlier, more celebratory phases of the spacecraft's journeys. Rather than deciding which new discoveries to pursue, they now found themselves in the more solemn position of deciding which existing capabilities to sacrifice, and in what order, carefully weighing the relative scientific value of each remaining instrument against the unforgiving reality of a power supply that would never again increase, only continue its slow, steady decline. The process began gradually, years before it became urgent, with instruments that had already completed their most valuable phases of operation being powered down first, freeing up small amounts of electricity to help sustain other systems considered more essential to the mission's continuing scientific goals. Heaters warming instruments no longer in active use were switched off. Backup systems, redundancies that had been built into the spacecraft's original design specifically to guard against unexpected failures, were increasingly retired, not because they had failed, but because the spacecraft could no longer afford the electricity required to keep them ready. There is something quietly moving in this particular aspect of the mission's later years, a kind of institutional patience and care that mirrors, in its own way, the same meticulous attention that had gone into the spacecraft's original design decades earlier. The engineers making these decisions were not simply managing a technical decline. They were, in a very real sense, tending to something they had inherited, often from mentors and colleagues who had since retired or passed away, carrying forward a responsibility to extend these spacecraft's useful lives as thoughtfully, and for as long as the unforgiving physics of radioactive decay would possibly allow. Each instrument shutdown carried its own particular scientific cost, weighed carefully against the benefit of preserving power for other systems. The cameras, as discussed earlier, had already been permanently retired following the capture of the pale blue dot photograph, their power redirected toward instruments considered more valuable for the spacecraft's ongoing work in the unfamiliar territory of interstellar space. Other instruments followed in subsequent years, each shutdown representing the permanent loss of some particular kind of perception, some specific sense through which the spacecraft had once perceived its surroundings, now going dark one by one in a process that mission scientists sometimes described with a certain somber precision as the spacecraft gradually losing its senses. It is worth pausing on this particular framing, because it captures something essential about how these decisions were actually experienced by the people responsible for making them. This was not simply the routine management of a depleting battery, the kind of mundane, technical challenge that might apply equally to any piece of ordinary consumer electronics. These were choices about which of the spacecraft's original capabilities, which of its carefully engineered proxies for human perception, would be allowed to continue functioning, and which would be permanently silenced in service of extending the life of whatever remained. Some instruments were shut down not because their scientific value had diminished, but simply because their particular position within the spacecraft's overall power architecture made them among the least essential to preserve, once every remaining system was weighed against every other. Heaters for instruments no longer providing critical data were allowed to cool, exposing components to temperatures far colder than they had ever been designed to tolerate. Components that, once cooled this drastically, would very likely never function again, even if power were somehow restored to them later. This meant that each shutdown decision carried within it an unusual kind of finality, not merely pausing an instrument's operation, but effectively ending it forever, a one-way threshold crossed with full awareness of its permanence. Throughout this long, careful process of managed decline, both spacecraft continued remarkably to transmit valuable scientific data back to Earth, information about the character of interstellar space itself, the density and composition of the material surrounding the spacecraft now that they had left the sun's own protective bubble entirely, measurements that no other instrument anywhere has ever been positioned to gather directly. Even as their capabilities steadily narrowed, both spacecraft continued to accomplish genuinely unprecedented scientific work, a testament to how much value remained available even from instruments operating at a small fraction of their original design capacity. There's a particular kind of dignity in this extended twilight, one that distinguishes it clearly from simple obsolescence or failure. These spacecraft were not being allowed to decline through neglect, nor were they continuing to operate through some accident of unexpected durability alone. Their extended lives represented a deliberate, ongoing act of careful stewardship, a continuous series of thoughtful decisions made by engineers determined to extract every remaining possible year and every remaining possible discovery from machines that had already vastly outlived every original expectation placed upon them at launch decades earlier. As the years continued to pass, following both spacecraft's historic crossings into interstellar space, mission engineers found themselves increasingly engaged in a kind of careful, ongoing triage, extending wherever possible through creative reallocation of the spacecraft's remaining power, whatever scientific operations still remained feasible, while gradually, gently allowing other systems to finally rest. It was, in every meaningful sense, a slow, respectful fade, rather than any sudden, dramatic ending, extended across years through nothing more than careful attention, technical ingenuity, and a quiet, sustained commitment to preserving, for as long as physically possible, the continued voice of two remarkable machines that had already traveled farther and endured longer than anyone involved in their original construction had ever dared to fully promise. Eventually, though, even the most careful stewardship would reach its limits. Somewhere ahead, at a point that could be estimated but not precisely predicted, the last remaining instrument would fall silent, and the final, faint radio signal, still carrying humanity's voice across the vast interstellar distance, would eventually cease as well. What that final ending might actually mean, both for the spacecraft themselves and for the generations of scientists and ordinary people who had followed their journey so closely, remained a question that mission planners had, by necessity, already begun quietly considering. There's a question that arises naturally from everything we have followed so far, one that becomes increasingly difficult to avoid the closer both spacecraft draw toward the outer limits of their operational lives. What actually happens in the end when the plutonium heart finally grows too faint to power anything at all? What does it mean precisely for a spacecraft this far from home to fall silent, and what, if anything, continues afterward? The honest answer offered by the scientists and engineers who understand these spacecraft most intimately involves less drama than one might expect and considerably more quiet physical continuity. There will be no dramatic final moment, no last burst of activity before sudden, complete silence. Instead, based on everything currently understood about the gradual decline of each spacecraft's power supply, the ending will likely resemble everything that has come before it across these recent years. A continuation of the same slow, patient fade instrument by instrument, until eventually, sometime in the coming years, the very last operational system, quite possibly the transmitter itself, the device responsible for sending any signal back toward Earth at all, will finally lack sufficient power to continue functioning. At that point, communication will simply stop. There will be no final message, no dramatic farewell transmitted in some symbolic final broadcast. The radio signal, which has traveled faithfully across billions of miles for nearly 5 decades, carrying with it humanity's ongoing dialogue with its most distant proxy, will simply not arrive on its next expected occasion. Scientists monitoring the signal will notice its absence, will attempt, likely for some time afterward, to re-establish contact, adjusting their sensitive receiving equipment in case some faint, degraded signal might still be detectable. Eventually, after sufficient attempts have failed to produce any response, the mission will be formally declared complete, not through any single decisive event, but through the accumulated absence of a voice that had, for so long, remained remarkably, faithfully present. This moment, whenever it eventually arrives, will mark something genuinely significant in the history of human exploration, the end of active communication with the farthest traveling objects ever created by human hands. But it is worth being precise about exactly what will and will not actually end at that point. The spacecraft themselves will not stop existing. They will not disintegrate or combust or otherwise cease their physical presence within the universe. They will simply continue, exactly as they have been continuing all along, drifting outward through the vast emptiness of interstellar space, their trajectories unaffected by whether or not any instrument remains capable of communicating that continued journey back to Earth. This distinction matters considerably because it reframes what the eventual loss of communication actually represents. It is not the end of the spacecraft's existence, but rather the end of our own ability to continue listening to it. The spacecraft's journey will continue regardless, carried forward by the same patient laws of physics that have governed its trajectory since the moment it first left Earth's gravity, decades earlier. What will actually end at that final moment of lost communication is not the voyage itself, but our own participation in witnessing it. This reframing invites a particular kind of reflection about what these spacecraft will actually become once they have passed beyond our ability to hear from them. They will continue moving outward, carrying their instruments, their now silent radioactive hearts, and their golden records indefinitely through a region of space so genuinely empty that meaningful encounters with any other object become almost unimaginably rare. Current calculations suggest that neither spacecraft is likely to make any kind of close approach to another star for at least tens of thousands of years. And even then, close approach in this context still involves distances measured in trillions of miles, an encounter close only by the almost incomprehensibly vast standards of interstellar space itself. In this sense, both Voyager spacecraft are destined to become something considerably stranger, and in certain respects considerably more permanent than almost any other human creation. Nearly everything else built by human hands exists within environments that actively work to degrade and eventually erase it. Buildings crumble under weather and time, books decay unless carefully preserved. Even the most durable earthbound monuments, built specifically to endure for centuries, exist within an atmosphere, a climate, a biosphere that continuously, patiently works to wear them down. Interstellar space offers no such active forces of decay. There is no wind to erode a spacecraft's surface, no rain to rust its components, no atmosphere at all to gradually break down its structure through oxidation or weathering. In the near-perfect vacuum through which both Voyagers now travel, the primary forces capable of damaging a spacecraft, occasional impacts from tiny particles of interstellar dust, or the slow, cumulative effect of cosmic radiation operates so gradually across such vast expanses of both space and time that both spacecraft are expected to remain largely physically intact for an almost unimaginably long period, quite possibly for hundreds of millions of years, and by some estimates, potentially for a span of time comparable to the current age of our entire solar system. This is a claim genuinely worth pausing on because its implications extend so far beyond any time frame ordinarily considered in discussions of human achievement. Human civilization itself, in its current recognizable form, has existed for perhaps 10,000 years. Recorded history spans a period shorter still. And yet these two small spacecraft, built by a relatively narrow window of engineers working across a handful of years in the 1970s, may very well continue existing, largely unchanged, for a length of time that dwarfs not just the whole of recorded human history, but potentially the entire span of time that our own species has existed on Earth at all. There is something quietly staggering in this realization, one that reframes everything we have followed throughout this spacecraft's journey. What began as an ambitious but relatively modest scientific mission, designed originally to study a handful of planets across a rare, favorable alignment, has become something considerably larger in its ultimate scope. Two of the most durable objects ever created by human beings, destined to persist largely intact for a length of time that may well exceed the survival of our own species, our civilization, quite possibly even our own planet's continued habitability, depending on how far into the deep future one is willing to extend such speculation. This raises a particular, almost dizzying question, one that mission scientists themselves have occasionally allowed themselves to consider, even if only briefly, amid the more immediate, practical concerns of actually operating the spacecraft. If both Voyagers genuinely are likely to persist for such an extraordinary length of time, considerably longer than human civilization has yet existed, what, if anything, might eventually happen to them in some almost unimaginably distant future should they ever actually encounter something or someone capable of finding them? This question moves us necessarily into a different kind of territory than anything discussed so far in this documentary, territory considerably more speculative, resting less on established scientific measurement and more on careful, informed reflection about probability and possibility. It is a question that circles back ultimately to that small golden record, still riding quietly along the side of each spacecraft, waiting patiently for a future that may never actually arrive, but which was, from the very beginning, considered important enough to prepare for regardless. Because if these spacecraft truly are destined to outlast nearly everything we currently recognize as human civilization, then the message they carry, prepared so carefully by scientists and artists working together across those early years of the mission, takes on a significance considerably beyond its original, more modest purpose. It becomes not simply a scientific curiosity or a symbolic gesture attached to an otherwise purely technical mission, but potentially the single most enduring message our species will ever produce. A message that might well outlast every other human creation, every book, every recording, every physical structure we have ever built, surviving quietly, patiently in the vast emptiness of interstellar space. For a length of time that stretches the imagination well past any ordinary human scale of thinking. It is to that message, and to the full story of everything it was designed to carry and to mean, that our journey now finally returns. Long before either Voyager spacecraft ever left the ground, before their instruments had been calibrated, before their trajectories had been finalized, a small group of scientists, writers, and artists gathered to attempt something that had never quite been attempted before. Their task, assigned relatively late in the mission's overall planning process, was deceptively simple to state and extraordinarily difficult to actually accomplish. They were asked to create a message, one capable of representing the entirety of human experience, compact enough to fit on a single phonograph record, and clear enough that it might, conceivably, be understood by an intelligence with no shared history, no shared biology, and no shared language with humanity at all. Carl Sagan led this effort, joined by a small team that included writer Ann Druyan, artist John Lommerg, and several other collaborators, each bringing a distinct expertise to a project that resisted, at nearly every turn, any single, obvious approach. How does one even begin to summarize an entire species, an entire planet, an entire history of joy and suffering and discovery, onto a single physical object small enough to travel comfortably aboard a spacecraft already carrying so much other essential equipment? The team eventually settled on a format that felt, in retrospect, almost inevitable in its combination of ambition and humility. A gold-plated phonograph record, chosen specifically for its durability, capable of preserving its contents essentially unchanged across an almost unimaginable span of time, accompanied by a cartridge and needle, along with a set of symbolic instructions etched directly onto its cover, attempting to explain, using only universal physical and mathematical principles rather than any spoken or written language, exactly how the record might actually be played. The contents ultimately selected for this record represent one of the most carefully considered acts of cultural curation ever undertaken, a project that required its creators to make impossibly difficult choices about what exactly deserved to represent all of humanity to whatever distant, unknown listener might someday encounter it. The team settled on 116 images, encoded onto the record in a format designed to be decoded visually, depicting everything from human anatomy and daily life to landscapes, architecture, and scientific diagrams, an attempt to convey, through pictures alone, something of what human existence actually looked like, across as broad a range of contexts as the limited space would allow. Alongside these images, the record carried nearly 90 minutes of music, drawn deliberately from cultures scattered across the entire world, rather than limited to any single tradition. Contained within the exact sequence carefully chosen by the selection team, though its specific content falls outside what can be quoted here, this collection was assembled with a specific intention. Recognizing that music might communicate something essential about human emotion and creativity, even to a listener who could understand nothing of the actual words or cultural context surrounding any individual piece, something felt more directly than explained, carried through rhythm and melody rather than through language that might mean nothing at all to unfamiliar ears. The record also carried a collection of natural sounds, recordings capturing something of Earth's own voice, quite apart from anything human, wind moving across open landscapes, waves breaking rhythmically along a distant shore, birdsong rising through early morning air, thunder rolling across a darkened sky. These recordings served a particular purpose within the record's overall structure, offering a listener not just a portrait of humanity specifically, but of the broader living world that had produced humanity in the first place, situating our species within a richer, more complete picture of the actual planet we call home. Perhaps the most quietly affecting portion of the record, however, consisted of spoken greetings, recorded in dozens of different languages, each speaker offering some simple, warm expression of welcome, intended for whatever unknown listener might someday actually hear them. These greetings ranged from formal diplomatic messages to remarkably simple, almost childlike expressions of hope and friendship, a deliberate choice reflecting the team's understanding that grandeur alone could not adequately capture what they hoped to convey. Sometimes the simplest, most direct expression of warmth carries considerably more genuine meaning than the most carefully composed formal statement ever could. Among these many voices, one particular contribution carries a significance that becomes especially poignant once properly understood. Included within the record's greetings is a brief message recorded by a young child, offered on behalf of the children of Earth more broadly. A simple, unguarded expression of welcome extended outward across the stars by someone too young to fully grasp the almost incomprehensible scale of the journey their small recorded voice was about to undertake. That voice, captured in a brief moment sometime in the 1970s, now travels through interstellar space, permanently preserved, a child's greeting extended toward a future, and toward listeners that remain entirely unknown, and will very possibly remain unknown for longer than human civilization itself continues to exist. There is something profoundly moving in this particular detail, one that captures, perhaps better than any other single element of the record, exactly what its creators were ultimately attempting to accomplish. They were not simply compiling scientific data about Earth, or even attempting some purely rational summary of human achievement and capability. They were attempting something closer to an act of genuine, hopeful tenderness, extended outward into a darkness so vast, and toward a future so uncertain that the entire gesture required a particular kind of faith, not religious faith exactly, but something closely related to it. A willingness to offer something precious, something deeply personal, without any real expectation of ever knowing whether it would be received, understood, or valued by anyone at all. This particular quality, this willingness to offer something so tender and hopeful into circumstances so genuinely uncertain, extends even further into some of the record's most quietly intimate contents. Among the sounds included was a recording intended to represent something universally understood across human experience regardless of language or culture. A mother's gentle expression of affection toward her child, a kiss, offered not to any particular individual, but as a representative gesture meant to stand in for the broader, deeply felt tenderness that exists between parents and children across every human culture throughout history. Consider what this particular choice actually represents when properly understood. Of every possible sound the team might have selected to represent human affection, they chose something this intimate, this unguarded, offering it outward not toward any specific recipient here on Earth, but toward whatever unknown listener might someday encounter this small golden disk, drifting through the emptiness between the stars. It is difficult to imagine a more vulnerable, more genuinely hopeful gesture than this, extending something so deeply personal, so entirely without any guarantee of appropriate reception, into circumstances so profoundly uncertain that its creators understood, from the very outset, they would almost certainly never learn whether their gesture had actually reached anyone at all. This uncertainty, in fact, sits at the very heart of what makes the Golden Record's true significance so difficult to fully capture. The scientists who created it understood with complete clarity that the record's chances of ever actually being discovered and understood by another intelligence were vanishingly small, a possibility measured not simply in unlikely odds, but in odds so distant that ordinary language struggles to adequately convey them. The record might drift through interstellar space essentially forever, encountering nothing, discovered by no one, its careful, hopeful message never actually heard by any listener at all, human or otherwise. And yet this near certainty of its message going forever unheard did not, in the end, prevent its creators from proceeding anyway, from pouring genuine care and consideration into every single element included on its surface. This choice reveals something quietly profound about the underlying purpose the record was always meant to serve, one that extends well beyond any realistic hope of actual extraterrestrial contact. Its true value, arguably, was never primarily about the remote possibility of eventual discovery at all. It was about what the act of creating it revealed about ourselves, about a species capable of looking honestly at its own considerable flaws, its wars, its cruelties, its ongoing struggles, and choosing nonetheless to represent itself outward into the universe not through those failures, but through its music, its natural wonders, its languages, its children's voices, and a mother's simple kiss. The Golden Record exists now, and will very likely continue existing for a length of time that dwarfs any ordinary human measure, as a kind of message in a bottle, cast into an ocean so vast that the chances of it ever washing up on any particular shore remain essentially negligible. But the record's genuine significance was perhaps never really about the destination at all. It lies instead in the sending itself, in what it reveals about a species capable of looking outward into a darkness offering no promise of reply, and choosing even so to speak. To say in whatever way it could, across however many silent centuries might pass before anyone, if anyone ever does, finally listens, we were here, we wondered, we loved. And for whatever brief moment we occupied this small, fragile point of light, we tried in our own imperfect way to reach outward, toward whatever else might be waiting for us somewhere out there in the dark.